Okay. We are ready now for the next. We are going to talk today about the natural logarithm function. Now, remember we did our exponential in terms of y equals e to the x, but we said y equals 2 to the x looks the same, y equals 7 to the x looks the same. All the exponentials look the same. Because we focused on y equals e to the x for exponential, we're focusing on the natural logarithm, but that would be the same. It would look the same if it were log. The shape of a logarithm is the shape of a logarithm, regardless of the base. We're just using a base of e. And that curve has an asymptote here and looks like this. And this is the point 1, 0. It is very closely related to the exponential, which looks like this. Do you see how it's kind of the reverse? And the exponential has an asymptote at y equals 0. The logarithm has an asymptote at x equals 0. The exponential contains the point 0, 1. The logarithm contains the point 1, 0. They're very closely related. All right, so here we go down our list. What's the domain of this function? 0 to infinity, and 0 is not included. Can you tell that? There's an asymptote there. 0 is not included. What that tells you is, whatever you put in for x, when you take the logarithm of something, when you say ln 5, ln 12, you can't do ln negative 10, because negative 10 would be over here, right? So, if you remember, and it was a passing comment, and you probably, well, some of you haven't even watched the video yet, but I said there are 3 things that impede domain. Can't have a 0 in the denominator, can't have the square root of a negative, and with logarithms you have to be careful. And why do you have to be careful with logarithms? Because you can't take the logarithm of a negative. All right, what's the range of this guy? All real numbers. Up, it goes all the way down, it goes all the way up. All real numbers is your range. Would you call that a continuous function? Yes. Would you say it is increasing or decreasing? Increasing on its entire domain. It's always going up as we move left to right. Does it have any of our special symmetries? No. Is it bounded at all? No. When we talk about bounded, we talk about ceilings and floors, okay? Not walls left and right. We talk about ceilings and floors. So is this a bounded function? No. Does it have any hills or valleys? Remember, extrema mean maxes and mins. There are none. Does it have any horizontal asymptotes? No, but it does have a vertical asymptote at x equals 0. End behavior. Now this is another one. We had one yesterday that there isn't any end behavior toward negative infinity, because you don't go to negative infinity. So there's only one end to look at. And what is happening to the curve as I head off the page, what is my curve doing? Going up, 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 up. So its end behavior is positive infinity. What this means is, as x gets bigger, so does y. It just keeps climbing. Now we got a couple that we're going to have to, I'm going to ask you to set up your grid a little specially. I would like you to maybe count up, what would be a good number, maybe 3 blocks and call that 1. and then likewise down here, -1. So we're just changing our scale a little bit. The entire sine curve happens between -1 and 1. So if you use those little blocks, it's going to be all squished up and tiny. Now let's use groups of 2. Yeah, let's use groups of 2 this way. So I'm going to have you label this pi over 2. This makes no sense to you right now, and that's okay. This is just how we're going to label our x-axis in both directions. So I'm skipping to spread it out a little bit. You may remember from last year, and I haven't talked to your teachers about this, so I don't know. Did you talk about radian measures last year, when you measure angles in radians? Did you talk about that at all? Okay, good. I'll get to teach you something. But right now, just take my word for it. This is how I want you to label these. These are angle measurements, believe it or not. Those are angle measurements. They're just measured not in degrees, but in a unit called radians. At this moment in time, that is not important, okay? What is important is you know the shape of this curve. All right, so here is what this curve looks like. You put a dot at the origin, a dot at pi over 2, 1, then another dot here, and then 3 pi over 2 is -1, and another dot here. Connect the dots with a nice smooth curve, no jagged edges. This is your sine curve. And I'm going to make you go the other direction. That is your sine curve. Now, it does go on forever and ever. We're not going to draw it forever and ever, but it goes on. So maybe I'll put arrows on the end here to indicate that. Okay, the sine curve is what we call periodic. It repeats itself. So you have a hill and a valley, and then if I kept going, I'd have another hill and another valley and another one and another one. It just keeps going forever and ever and ever. Periodic means it repeats. So this is our first curve that has a repeater in it. It repeats over and over. All right, so let's answer some of the questions. What's the domain? What's my x? All real numbers. Your domain is all real numbers. By the way, this is pronounced sine, not sin. So y equals sine x. And it's actually S-I-N-E is the full word, but we always abbreviate to 3 letters, so it's S-I-N, but it's sine x. So its domain is all real numbers. What about its range? -1 to 1, and those are bracketed, right? Because they are included. That is your range. Would you say the sine function is continuous? Yep, it surely is. Increasing or decreasing? It is both, right? Now, we could spend the rest of our lives, literally, writing down all the intervals where it increases and all the intervals where it decreases. So for the sine and the cosine, it's going to be the same situation. Let's just pick one period to look at. Let's just look at this part of the graph right here. One hill and one valley. And on that hill and valley, where are we increasing and where are we decreasing? We're only looking at this hill and this valley. So we're increasing from 0 to pi over 2. Remember, these intervals are x values. Increasing, decreasing, moving left to right, that's x values. So we're increasing from 0 to pi over 2. And actually, I'm going to go ahead and include that 0, not to freak you out, but aren't I actually increasing through 0? it's different than this point. What's happening at that point? I'm like, stopped. So I'm not going to include that one. Now, in that interval, that one hill and valley, are there any other places where I'm increasing? From 3 pi over 2 to 2 pi. And I'm going to include that 2 pi because I'm increasing right through it. Now, in that hill and valley, are there any decreasing intervals? From pi over 2 all the way down to 3 pi over 2? Now, most normal people are going to choose that hill and valley to look at. But could you do exactly the same thing with this hill and valley? Yeah, sure you could. All right, symmetry. Does this thing have any of our special symmetries? Is it symmetric about the x-axis? No, because if you folded it across the x-axis, it wouldn't be on top of itself. It wouldn't be the same picture. It would be a different picture. What if we folded it across the y-axis? No, would not be the same picture. What if we flipped it across the origin? Yes, so this has symmetry about the origin. So an important fact for you to remember is the sine is an odd function. There are 6 trigonometric functions. Thank you, Paige. There are 6. You need to pass? There are 6 trigonometric functions, right? Well, maybe you know that, maybe you don't. I'm assuming you know. Maybe you don't know that. There are 6 of them. And some of them are even and some are odd. They're all one or the other. And the sine is odd. So try to remember that. It's kind of important for later. Is this guy bounded? This is our first example of a truly bounded function. Because to be bounded, you have to have a ceiling and a floor. And we've had functions that had one or the other, but this one has both. Okay, so it is bounded. It's bounded above at y equals 1, and it's bounded below at y equals -1. Does it have any hills and valleys? Oh, infinitely many of them, right? So we're going to do the same thing we did before. We cannot possibly list all of the extrema. Do you understand that? This thing goes on forever and ever and ever. So let's just go back to that first hill and valley right here. What would you call the point pi over 2 comma 1? That point right there is the point pi over 2 comma 1. What would you call that? That is a local maximum, and it is also one of the absolute maximums, right? That's the high point. Now, could I say the same thing about this point? And this one, yes. We're just going to pick one. That is a local or relative maximum. It is also an absolute maximum. What about the point 3 pi over 2 -1? That's this guy right here. X is 3 pi over 2, y is -1. What about that point right there? What's he? He's a local minimum or an absolute minimum. Any asymptotes? Well, yeah, not really, because asymptotes are things we approach. Yeah. And we're not really approaching that, we're just bounded by that, so no. Sines and cosines have no asymptotes. All of the other 4, the trig functions are 6 altogether. Sine and cosine do not have asymptotes, all the other 4 do. Cosine is the only one we'll look at now, though. Okay? And then finally, end behavior. Tell me about the end behavior of this guy. We don't really have end behavior Because what do we keep doing? The farther out I go, what do I keep doing? Oscillating between 1 and -1. So I'm not really approaching anything, so we don't discuss the end behavior for the sine and cosine. We haven't gotten cosine yet, but the same thing will be true. Because it doesn't, it just keeps oscillating. The curve just keeps going up and down, up and down, up and down. It doesn't approach anything. All right, so now we've got the cosine function. I want you to set up your axis exactly the same for the cosine, okay? So we're going to count up and down 3. That'll be 1 and -1. I'm going to label these exactly the same way. And at this point, you just sort of need to memorize. That's how you're going to label it. I promise that in a few months that'll make such good sense to you, but right now we're just going to have to memorize that. And then I'll have you put some points on it, just like you did a minute ago. Remember, sines and cosines are nice, smooth curves. So we should not have any jagged edges, no V's or points, just nice, smooth curve. This is the cosine function, which is COS. The equation is COS, cosine. Now, as we're waiting for everybody to catch up, I know this is different and new to you, so we'll just pause for a second. But while we're waiting for everybody to get that drawn, kind of think about all these things. Are there some similarities with the sine? What about domain and range? What's my domain? All reals, just like the sine, right? What's my range? -1 to 1, just like the sine. In fact, are these like almost exactly the same curve? Yeah. What happened? We took that one and shifted it. So that won't change the domain and range. How about continuity?
Yes.
It's all good. Now, increasing and decreasing, that's going to change, right? So let's look at, right here, this first time around the unit circle right there, from 0 to 2 pi. Let's look at that one. Where are we decreasing? From 0 all the way to pi? Isn't my pencil going down? If I look at this part from 0 to 2 pi, that stretch right there, is that where my pencil's going down? And then where am I increasing?
Pi to 2.
From pi to 2 pi. That's right. You can do the same thing over here. You're decreasing from -2 pi to -pi. You're increasing from -pi to 0. Remember, we're talking about moving left to right, so these are x's. What kind of symmetry does this guy have? Y-axis. So this is an even function. The cosine is even. It has symmetry about the y-axis. Found it?
Yes.
Yes. Above by y equals 1, and below by y equals -1. It's exactly the same as this one. Remember, you told me it was essentially the same curve, right? Does it have extrema? Yeah, infinitely many of them again. So let's just look in this part right here, like we did before. Oh, there's nothing sacred about this part. It's the part we normally look at because it's like the first quadrant area, but or the first period, the first spin around the unit circle. But we have to pick a section to look at. Otherwise, we can't just keep going and going with all these maximums. So, if we look at this part right here, the point 0, 1, now that's a point, not an interval. The point 0, 1 and the point 2 pi 1 are what?
Yeah.
Local and absolute maximums. Patty's your hand up?
No.
Just stretching?
Yeah.
And what point is this? This would be the minimum. What point is that? Pi negative 1, and that would be a
Minimum.
local and absolute minimum in that little stretch of the curve. You could do the same thing over here with these points. No asymptotes and no end behavior. It's exactly like the sine. It just keeps going up and down, up and down, up and down. Okay?
This is a lot to take in.
This is a lot to take in. But, like I tried to emphasize yesterday, these are the hardest to graph because you do not know these labels. But if you memorize the picture, Patty, the rest of it you can pretty much figure out. Okay. Now, here's how we're going to do the last 3. I'm going to give you the sketch, and then I want you on your own with your friends that are sitting around you, try to fill in all of the things from the pictures, okay? So I'm going to give you the sketches. Absolute value. Here's your equation. Absolute value looks like this. That's an easy one. I know for a fact you studied that last year, that curve. That's absolute value. The greatest integer function is my least favorite. And different books use different notations. I know. I'm going to go ahead and just use brackets and not that funky stuff. This means greatest integer. I do not like this function personally. It looks like this. I'm with ya. I am with you. There aren't very many things that make me moan and groan, but this is one of them. That's your greatest integer function. And the logistic function. Here's the equation of the logistic function. And here but you might want to make that a few boxes in there, you know, move that up a little bit, otherwise it's going to be all squished in there. Okay, so I have given you the equation, I've given you the graph for the ones on the last page here. So now I want you and your friends to start filling in. Tell me what you come up with in terms of domain, range, etc., etc.
The range is all reals, and then the range is, isn't it?
You mean the domain is all real?
Yeah, that's right. And the range is, because it can't go.
Right. But if you read it left to right.
Y is equal or equals to 0.
I always said y is greater than or equal to 0.
Yeah.
That's another
That's
one.
amazing.
I know. I don't think you would do that.
It's increasing.
Oh yeah, she was. Oh yeah, I feel like she was here. She was really quiet. 2 times I said no pulling. I don't remember that. No, we didn't have you.
There's no continuity. It's symmetrical, right?
It is continuous.
It's not just y, it's just
Okay. All right. How are you coming? Let's get this stuff filled in.
It's bounded.
is there no increase?
Below. There's an increase.
So it is.
That's what I thought.
But hold on. If you read it left to right,
I said increasing from 0 to infinity.
Yeah, that's what it's like the minimum to max.
yeah.
And then even symmetry on 1 over 2.
Is it bounded?
Yeah.
Zeros
Below.
Did we count that? No. We didn't count this one. It says minimum 0.
Okay, you should put that then.
Yeah, because this is going down, this is going up, and then this is going up.
Horizontal.
I don't even want to look at that one.
There's no
I don't even want
The bar.
That's just a bound.
to. Do you not remember doing this? Like, we literally spent like 1 day on this. I don't even remember how to do it. I just was like, it was so confusing.
It wasn't on the technicality.
I don't know.
So confusing. I was like, I want to do it, I don't want to do this. I remember like learning it about this. I don't remember how to do it.
I remember seeing it. I remember anything about it. What's the domain?
I have to know it.
For what? You can also stuff.
It is inclusive.
I have a starting exam today. I don't have the boat, so I'm not going to
Okay. Let's talk about these. Make sure we have time to discuss them all. Let's see what you came up with. So let's start with absolute value. Okay? Now, I want you to think about one of the other functions we've had that looks an awful lot like this. X squared. Do you think probably that everything we said about y equals x squared is going to be true about this one? In terms of everything. Same domain, all real numbers. Range, y greater than or equal to 0. So the range is 0 to infinity. What about continuity? Continuous. What about increasing or decreasing? Well, it's increasing from 0 to infinity, and it's decreasing from negative infinity to 0. No, because what's happening at 0?
Change of direction.
It's stopped, it's changing direction. So if you were gonna include 0, you'd have to include it in both places. And then you say, how can you be increasing and decreasing at the same time? You can't, you're stopped. Symmetry, y-axis, this is an even function. Boundedness, bounded below at y equals 0. It has a floor, in other words. Local and absolute extrema, you have a minimum. It is a local and an absolute minimum at 0, 0. Right? No asymptotes. And then end behavior for the absolute value function, end behavior, positive infinity to the right, and positive infinity to the left. Everybody okay with that? Heading to positive infinity on both sides. Alright, so we good on that one? Alright, now we come to the greatest integer function, domain. All real numbers. Every x is accounted for. Now the fact that we're skipping around does not mean that we have not included an x. Every x is included all the way. So the domain is all real numbers. Now, what about the y's? Is every y included? No. Just certain y's are included. What is the y value here? 0. What is the y value here? What is that? That's not all the y's, that's just the y's that are integers. So your range is the set of integers. Your inputs are anything. Your outputs have to be integers. That's why it's called the integer function. Continuous. Absolutely not. This one has what is known as jump discontinuity. Now, we talked yesterday about removable and non-removable discontinuities. What's a removable discontinuity look like graphically? You had one on your quiz. No, a removable. A removable is a hole, because you cancel it out. A non-removable is a vertical asymptote. Well, then we also have this weirdness in some problems where the curve is simply jumping. You have to pick up your pencil and you jump. It's not because of an asymptote or a hole, it's just the way the curve is structured. So this is called jump discontinuity. Remember, discontinuity means you have to pick up your pencil. You have to pick up your pencil if you have an asymptote. You have to pick up your pencil if you have a hole. You have to pick up your pencil if you have steps. So it's discontinuous. It has jump discontinuity. Increasing or decreasing? Now you have to be really careful about this, because what's happening on this piece?
It's going straight.
It's not increasing or decreasing, right? What about this piece right here? This piece right here. It's really, I know what you think when you look at it. You think it's an increasing function because the steps are going up. But is the entire curve increasing on any interval? No, it's that jumping again. So I would just say neither for this one. Does it have any kind of symmetry? No, because if you flipped it, the steps would be reversed. So no, there's no symmetry. Is it bounded above or below? Nope, just gonna keep going. No hills and valleys, no extrema. No asymptotes. Now, it does have end behavior. So, I'll write the end behavior over here. It does have end behavior. What's happening as we head off the page on the right side? What is happening to my greatest integer function? What's happening to the y values? They are getting bigger. And what's happening? They're going negative. So as we go, as x marches on this way, y marches down that way. And then the logistic function, which is a very valuable function, especially like studying populations. This is a very valuable tool. Okay, so tell me about the logistic function. Domain, all real numbers. Range, 0 to 1, and they are not included. So it's with the sine and cosines, we use brackets because they were included. These are both asymptotes, not included. That's your range. Would you call that a continuous function? Yep. Would you say it's increasing or decreasing? Increasing on its entire domain. That's right. Does it have any symmetries? No, it does not. Now, it has a unique point of symmetry, but that varies from curve to curve, so we're not going to discuss it. In terms of our special symmetries, it doesn't have any. Is it bounded? Yes. Absolutely. It is what we call a bounded function because it is bounded above at y equals 1 and bounded below at y equals 0. Does it have any hills and valleys? No. No extrema. Does it have any horizontal asymptotes? Yeah, 2 of them. One at y equals 0 and one at y equals 1. Does it have any vertical asymptotes? No. But it does have end behavior. So let's think about this now carefully. Remember our end behavior, we're taking the limit as x approaches positive infinity, that means that way. And as x approaches negative infinity, that means that way. Now tell me what's happening as the curve marches this way. It's getting closer to 1 from the bottom. So I will write 1 with a little negative sign here. That tells me I am approaching 1 from the bottom side.
What do you mean by the bottom side?
I can approach 1 like this. Here's 1. This is the top of 1. This is the bottom of 1. I'm coming in underneath it. Now, what about as I march this way? It's getting closer and closer to 0 from the top. Ooh, okay. Now, keep that sheet handy because I'm going to ask you a couple questions now about that. Okay, so you got your sheet. Let me ask you a few questions here. Oh boy.
Yeah.
And that's a tricky one. That's a tricky one. Okay. All right, here we go. One of our new functions, absolute value. What's the shape of an absolute value? V. Right, the V. Now, the normal function is vertex at the origin, looks just like that. That's the normal absolute value. I stuck some extra numbers in here though. We need to know what those numbers do. We talked about this before, but I never put two of them in the same problem. Okay? Now, if the number is grouped with the x, then it moves left and right, the opposite of what you think. So x minus 3 is actually going to move you to the right, 3 steps. If a number is tacked on the end of the problem, not grouped with the x, just stuck onto the problem, it moves you up or down, and it does exactly what it looks like it's going to do. So if that says plus 2, that means we're going to go up 2. So you're going to have your exact same V. It's like cut it out and paste it so that the vertex is at the point 3, 2. Does that make sense to everybody? Now, doing that will not change the domain. Isn't the domain still all real numbers? But it will change your range. Because in the beginning, the parent curve, the basic family curve here, the range is greater than or equal to 0. Now it would be greater than or equal to 2. That's not hard to understand, right? You got that. All right, sine function. Now, you may have memorized this because I told you it was kind of important, but if not, just think about the curve. Look on your sheet. I know you don't have it memorized yet. That's your sine curve. Now, what does it mean to be even or odd? It means it's got to have symmetry about the y-axis. Does this have symmetry about the y-axis? No. Or symmetry about the origin. Does this one have symmetry about the origin? No. Oh, yes, it does. Oh, yes. Yes, it does. If you took each of these points and flipped them across the origin, they would come right back on themselves. So that is an odd function. The sine is an odd function. It has symmetry about the origin. Remember, sine is odd, cosine is even. That'll be important later. Now, I don't know that we've talked about these negatives. Maybe we have, I can't remember, so we're going to talk about them again. If you add and subtract numbers, that physically picks you up and moves your graph. What do negatives do? They flip you, they reflect you. And there are, just like there are 2 places I can put numbers, there's 2 places I can put negatives. If the negative is out in front, of the function, it turns it upside down. So, I'll write it this way. If it's out in front of the function, it turns you upside down, which is just kind of a common sense way of saying you flip across the x-axis. So this normal curve, parabola, looks like that. But because I put a negative in front of it, it's going to turn it upside down. Now that's a concept you're familiar with, right? A negative on the x squared turns it upside down. It's going to turn everything upside down. So if you put a negative in front of your absolute value, you're going to have a v going down. Now what if the negative is grouped with the x? If the negative is grouped with the x, I guess I'll just use that one. If the negative is grouped with the x, it reflects or flips across the y-axis. well, wait a minute. What happens if I flip this, this is my squaring function. What happens if I flip it across the y-axis? Isn't it the same picture? Doesn't that make sense? That it would be exactly the same picture? Yeah, so it's going to be the same, it's an even function. It's symmetric about the y-axis, so when I reflect this one, it's not going to make any difference. I'm trying to think of, what if we had, this one. Now remember, y equals ln x looks like this. So when we put a negative on the x, it reflects across the y-axis. When you change the sign on x, you end up on the other side of the y-axis. So if I took that picture and flipped it, I would get this. Would you agree with that?
Yes.
There is a picture of that. Where we put the negative is just as important as where we put the numbers. If the negative is grouped with the x, you flip across the y-axis. If the negative is out in front, then it flips across the x-axis, upside down. Okay, got it? Okay, well, you're gonna love this news. Tomorrow I have you tomorrow, don't I? We're gonna have another little quizy tomorrow, and it's going to be much like the one we had. I'll hand this one back first. We'll go over this one first, the one we just took. It's gonna be much like the one we took today, except instead of focusing on just 6 functions, it's gonna focus on 12, all 12. So you will have questions about all 12, okay? So, what are we gonna make sure we know when we walk in here tomorrow? Well, you don't need to know everything about all 12. What do you need to know? What they look like. That is fundamental. You gotta know, okay, if I have an exponential function, this is what it looks like. If I have a logistic function, this is what it looks like. And then you can answer the questions based on that, right? Okay.